Welcome to the deep dive. Today we're looking up, actually, at something pretty vital but maybe overlooked, two-phase primary pull-top assembly units.
Right. Sounds technical, I know.
It does. But basically, two-phase primary often refers to power distribution that's, not the big three-phase systems, maybe more for smaller industry or rural spots.
Exactly. And the assemblies themselves, they're the critical bits holding and guiding the power lines.
Yeah, and the sheer variety is amazing. We're going to use some technical drawing numbers like VB1.111 sort of as our map today.
It's a good way to see the specifics. Our mission really is to decode these different types based on those drawings. Understand why they're designed the way they are, safety, efficiency, it's all in there.
Okay, so let's zoom in. The single support on crossarm units, we see VB1.11 and VB1.12 labeled tangent. What's that tell us?
Tangent generally means the power line is running in a pretty straight line at that point, no major turns.
But then you have VB1.11P and VB1.1P, and they specifically say post insulators. Why the difference?
Ah, right, post insulators. Think of them as more rigid. They handle sideways forces better than, say, hanging suspension insulator.
Oh, okay.
So you might use them for maybe slightly higher voltages or where you need extra mechanical strength. Even environmental stuff like pollution can be a factor. They resist flashover better sometimes.
Got it. That makes sense. We also see a VB1.13 for general single support, and it's P version 2. And then VB1.14 and VB1.14P add neutral on crossarm. How significant is adding the neutral wire up there?
Oh, it's very significant. That neutral provides the return path for the current. It helps balance the electrical load on the system.
And safety, I imagine.
Absolutely crucial for safety. It provides path to ground, helps prevent overvoltages, protects equipment. It's fundamental.
Okay, so if single supports handle the straight runs, when do you need to, double down? With double support on crossarms, like VB2.21 and, again, the VB2.21P with post-insulator.
Right. Double supports come into play when the forces are greater. Think heavier conductors, maybe.
Or longer gaps between poles.
Exactly. Longer spans mean higher tension on the lines, or sometimes you just need that extra stability, perhaps in areas with high winds or heavy ice loading potential. A single support just wouldn't be robust enough.
And we see the neutral wire appearing here, too, with VB2.22 and VB2.22P, double support, neutral on crossarms.
Yep, it's that consistent theme. Whether single or double support, managing that neutral path correctly is always part of the design for safe, reliable operation.
Makes sense. Now, what about when the lines aren't going straight? We have things like VB3.1, a suspension angle, and then VB4.1, a deadend angle for turns between 90 and 150 degrees.
Good distinction. A suspension angle is more like guiding the line through a turn. The insulators hang, allowing some flexibility while managing the angle.
Okay.
But a deadend angle is different. It has to handle the full tension of the conductor pulling from one direction and redirect it. It's anchoring the line tension at the angle. Much higher stress involved.
Ah, I see. So deadend implies managing that pulling force directly, which brings us to the single deadend units like VB5.1, VB5.21, VB5.31. These sound like termination points.
That's exactly what they are. A deadend is where the line physically stops on that structure or where the tension needs to be completely held before maybe going underground or connecting to equipment.
Like the very end of a line section.
Precisely, or sometimes between very different types of line sections. They are designed to take the full brunt of the line's tension under all conditions, wind, ice, everything. They're critical anchors.
And if one deadend isn't enough, there's VB6.21, double deadend on crossarms.
Right. That indicates an even more demanding situation. Maybe you have multiple heavy conductors terminating there or just exceptionally high tensions involved. It's about distributing that massive force safely across a more robust structure, the real heavy-duty termination setup.
Wow. When you break it down like that, the level of specific engineering in just these pole top parts is, it's kind of incredible, things you walk past every day.
It really is. You start seeing the built world differently, don't you?
Definitely. Makes you wonder.
It does. And maybe that's the thought to leave you with. How many other completely unseen, highly specialized bits of engineering are working constantly, perfectly, just to support the systems we take for granted every single day? What other hidden marvels are out there making modern life work?